lot for joining today. Once again, this is the third part of the day, porting applications, meaning porting from CPU, GPU to the IPU. I plan to cover Keras and PyTorch, relying mostly on the tutorials that we have in the public repository of examples. So again, at the high level, we support all these frameworks, going through different components of the software stack, and tutorials and code examples is what I'm going to touch a bit more during this session. And again, I would want to point to the videos that talk through some of these key concepts when porting applications or getting started with IPUs. In terms of the Keras, I've shown this example in the previous section, and I will be using tutorials in this repository. So let me just go ahead and open it. And I put down a sequence of commands to execute the same tutorials in this Google document with a human readable short link. So bit.ly ALCF 2406, which is this year, this month. So hope it helps. The document contains a set of steps to set up the environment for the tutorials, and then a set of steps to run those. And this is for tomorrow, for profiling session. So in order to set up an environment, I will, clone the examples, which is a public repository. I will create a virtual environment with, say, Python version 3.8 in this case. And inside of, or into that virtual environment, I will install a few wheel files that are a part of the Poplar SDK, which is preloaded on the Argon systems for everyone to use in this directory. So I've actually already done that. So maybe I will not spend a lot of time on setting up and installing the wheels, but the wheels include the PyTorch, TensorFlow, and Keras. Please note that TensorFlow wheel is specific to the to the CPU vendor, AMD, in case of ALCF. So the host servers have AMD CPUs in them. And another set of commands, the last 3 lines here in this setup section, enable caching of the executables on the system, so that when you run a program in PyTorch, if you have this environmental variable set up, the binary that the compiler produces will be stored in this directory. And the next time the compiler tries to execute the same, run the same graph, it will first try and look up in the cache. And instead of compiling, it will just load the binary from the cache. And similarly with TensorFlow, the command looks like this. So opening the tutorials, and maybe let me go from the Graphcore website. On the Graphcore website, you want to get to the developer page, which can be done by clicking here on the top menu, developer, and developer. So here you will have quick start documentation pieces and a few other options to dive into. This is a set of detailed documents on how to use IPUs and use machine learning frameworks like TensorFlow and PyTorch. There will be user guides and some notes on optimizing the execution on IPU in TensorFlow or PyTorch, including, say, memory optimizations. And tutorials cover some of those as well. So I can go to the tutorials here, and it's almost the same link as, well, probably not this one, as examples. This Graphcore GitHub will be a high-level public repository that contains examples and quite a few other things, Poplar libraries and high-level frameworks, open sourced. But for the tutorials, I want to dive specifically into the examples, and inside of the Graphcore/examples, I go to tutorials. There will be simple applications, feature examples, and we will start with tutorials inside the tutorials folder, and specifically TensorFlow Keras basics. Every tutorial here has a very nice README, which describes the steps that you need to take to understand what it means to take a program from, say, CPU and start running it on the IPU. In this case, the Keras tutorial starts with a program running on CPU, which is dedicated to training a simple CNN on the MNIST dataset. So we simply produce the tensors for the training and testing data, X and Y pairs, and we build the model by sequentially, well, chaining the layers, convolutions, max pooling, and then the classification layer with the softmax activation in the end. And we then use the functional interface of Keras to build this model, which is then on the CPU compiled using the SGD and the cross entropy as the optimizer and the loss. It prints, this simple example prints out the model summary and then goes through the steps of training and running evaluation with this model. So the summary looks quite simple, and the training will produce an output like this with a few milliseconds per step. And yes, some other parameters here. Now, very simply, porting it to the IPU, as described here, involves importing the Python, so the IPU model of TensorFlow.python, which is defined inside the TensorFlow wheel file that we have just installed. And one of the optimizations that we want to introduce is to make sure that all the batches are the same size. We can do it by either padding the last batch and masking out the loss for the padding elements, or we can just crop the data set to make sure it is divisible by well, say the batch size, for example. And in this case, this is exactly what is done here. We make sure the training data set and the inference data set, its length, their lengths are divisible by the batch size, which is calculated here, given the batch size. And then we configure the IPU system in TensorFlow. In this case, well, it does request a single device from the system. Yeah, that's a good idea. Let me just share this link without the bit.ly part. And GitHub repo, yes. So there is another option that is used here, which is device connection type on demand, which means that while compiling, it will not allocate it will not grab and hold the device. It will compile and then attach to the IPU after the compilation is done and it's ready to run. And then it produces the device using this strategy, which is typically used for distributed training in TensorFlow or inference across several devices. And it puts the computational graph as it's constructed inside the scope of this strategy. So it's put on the device there, on the IPU device created by TensorFlow. I should say TensorFlow IPU device. And then the execution of this program is now offloaded to the IPU. It's slightly faster, but not much. And the next optimization that we want to introduce is the loop on the device, which is done by the standard argument in Keras's model.compile called steps per execution. It is used by TPUs as well. So it's an API within Keras that we just leverage for the IPU. And we specify the steps per execution in a variable. We ship it to the model.compile here in this argument. And the important piece is to make the dataset divisible now by not only the batch size, but the steps per execution as well. And now with more than one step per execution, the time per step has reduced by an order of magnitude. So from 2 to 0.2 milliseconds, which is what we wanted. And with this, you can already be quite efficient. This is the main optimization to get up and running on the IPUs in Keras. Some of the other things are described here. For example, if you want to run data parallel with several replicas, you can do it by specifying the number of replicas in the IPU config. Instead of one IPU, you request 2 in this example. And again, you make the training dataset's length divisible by the effective batch size per replica times the number of replicas. And this is again done to make sure that there are no incomplete batches in the training or testing dataset. And with this optimization, during the training of the model, you will see that you introduce data exchanges between the devices. As you do the gradient step, the gradients are computed independently on each IPU, but then you need to reduce the gradients on all the devices, which creates an overhead. So the execution time will go slightly up because of this overhead potentially. I should say that it goes up per step, but the effective batch size per step is also twice as high here. So overall, we have achieved speed up by running across 2 IPUs in this case. What you can do to reduce or amortize this overhead of data exchanges between the devices running data parallel is accumulating gradients from more than one batch before doing the gradient step. And there is a parameter for that. But this tutorial goes into pipelining, which is a technique that is used exactly as someone has asked before, to make larger models, models that do not fit on a single device because of the memory limitations, run it across more than one device. During pipelining, layers of the neural network, in this case, are divided across, say, 3 or 4 IPUs. This is for simplicity. We just created a picture with 3 IPUs so that the backwards pass and the forward passes are executed going down and up the chain of IPU devices. And there is a bubble, typically the pipeline bubble, that can be larger if your pipeline depth is longer, and the gradients are accumulated across all the batches that you put in the pipeline before you apply the gradient update in the end of the pipeline. So there is a balance. The more gradient accumulation you're using, the more you amortize the overhead of doing the data exchanges between the replicas, but you will also see that maybe you introduce some other trade-offs, like your gradients are now less noisy, but you need to do more steps to achieve the same loss or accuracy when running with the larger batch sizes. So gradient accumulation is described here below, and in this case, we combine the several techniques here: gradient accumulation, replication, and pipelining to make it all run together. The pipelining can be done by either making annotations of like which layers belong to which pipeline stage using this with the constructs in Python, or it can be done after you build the computational graph, after you build the model. For example, if you download a ResNet 50 model from the standard Keras repository of the models from the hub, you can pipeline a model built by someone else, I mean, defined in someone else's script, and still annotated to run with pipeline stages. And it's described in the documentation for TensorFlow and Keras. I will not touch on it in this talk, but let me know if you need it. Please feel free to reach out over email or Slack. I'm happy to describe that. So, and then the execution output is shown here with all those optimizations and tricks. So it's straightforward to follow this set of steps. Let me try to do that actually here. And let me keep the document on the other screen for reference. I have the examples downloaded in the, let me just make it, actually, Graphcore examples directory here, and I'm specifically interested in tutorials, TensorFlow 2, Keras, tutorial here. So all the optimizations are combined inside of this demo code only Python script. And in order to run that, I would do, well, since we need to request an allocation of IPUs from Slurm that controls the system here on ALCF pod 64, I would go and request it from using the srun command and specifying that I need the number of IPUs equal to 2 for this demo. And then I go Python code only. So I made a mistake here. I did not activate the virtual environment, so it probably will break on me, which I want to correct right away. My virtual environment was in that same directory as I have in the document that I've shared. Maybe for illustration, the modules I have installed here include, well, PopTorch, TensorFlow, and Keras, of course, and a few helper modules like NumPy and others. But these are basic modules that are easy to install with just pip. The command, the job that I have launched is queued. I am requesting 2 IPUs here, and out of 64, that means 32 jobs like this can be run in parallel. And I can try and do that. I can try and run a program that actually will monitor the IPUs that are in use. If I can create another session. And say, run the DC monitor command, it should print out all the IPUs that are currently being used by the users of the system. So you can see that as I executed the script, the Slurm allocated 2 IPUs, executed the CPU program, and now executes the program on the IPU with no loop on the device in this case. So it's a little bit slow, but still faster than on CPU, of course. And as it proceeds, maybe I will come back to this later, the loop on the device will speed it up further, etc. I want to mention that in the repository here, in the completed demos, there are 4 scripts that if you if you run those in Visual Studio, for example, or another IDE, you can compare the changes between the scripts. So what has changed exactly when we introduced the loop on the device or replication. And as an example, like this is a nice way to compare the files and see the important changes between the steps in the tutorial. Something like this would be helpful. So the difference between demo IPU and demo faster will be in these steps per execution that are introduced here. And passed as an argument to model.compile. So I think it's quite helpful to view it this way as well. So let me know, please, if you have any questions with this. And I can comment that after this no loop on the device example, the next example is with a loop on the device, which is faster significantly in terms of the microseconds per step. And then with replication, the batch size is larger. The time per step is a little bit higher as well, but overall we are running faster. And then the further examples with pipelining are also executed here. The goal in this one was not to optimize for speed, but to show how pipelining can be done. So if there are no questions so far, and feel free again to reach out at any point after the talk. Yes, do IPUs talk to each other through MPI? No. The communications between the IPUs are, first of all, done through what we call IPU links. I had a picture on the previous in the previous deck, and these are all scheduled statically by the compiler. So it's not MPI, it's the compiler moving the data between the IPUs similarly to the way it does between the tiles on a single IPU. During the exchange phases of the BSP sequence. The nice thing about Poplar is that when you allocate and target more than one device, say if you're targeting 2 IPUs, you will have all the available tiles across the 2 IPUs as a single address space that you can put your codelets and tensor slices on. And then the compiler will take care of moving the data between those. So it's not MPI. At some level of sophistication, you can use multiple instances of Python processes to run a program across, say, more than one CPU nodes. And then you can use tools like Horovod to aggregate metrics like accuracy across several processes like that. So that would be more configuration where MPI is helpful. If I have an AI model that is not parallelized, how many hops or nodes can I put it on? The minimum granularity is 1 IPU, if you're asking about that. Granularity of allocation. But a model that is not parallelized. Typically, well, maybe I'm not understanding the question, but typically you can extract some parallelization from neural network-based models. So switching from the Keras tutorial to PopTorch, the key point is to, well, wrap the training model with the loss using this training model construct of PopTorch, and similarly for inference. So you just import the PopTorch package, and it offers optimized data loader classes and other things, optimizers as well, that can be targeting IPUs more efficiently. For example, enabling that loop on the device. There are also asynchronous data loaders among the functions there in the PopTorch data loader API that are nice to use when the CPU is the bottleneck when preparing the data. The examples that I think are relevant as tutorials are shown on this slide, going through the basics where you wrap the model using the PopTorch's training model and inference model. Mixed precision discusses how you can increase the speed of your execution by switching, say, from single precision FP32 to FP16 for the metmals, maybe for model weights, as well for master weights, and also for the partial accumulation precisions in matrix multiplications as well. The efficient data loading tutorial is a really nice one that discusses the bottlenecks that can happen, that can be observed in some typical scenarios where the CPU would struggle to produce the data batches quickly enough for the accelerator to consume it. And it will go talk through the asynchronous data loading options. And pipelining covers the same topic of distributing the layers across more than one IPU, but in PyTorch, which is very similar to the Keras case that we've already observed. Let me quickly run through those because I realize I'm running over time again. Apologies for that. The basics, again, the README file in every tutorial directory is very helpful and clearly written typically. So it discusses what's PopTorch, once again, how it's structured, how you can train a model on IPU by using this training model to wrap around and extract the graph and build a backwards pass. And it builds this simple model. It is based on actually the Jupyter notebook that you can run step by step. So it's an extract. The README is an extract of from the Jupyter notebook in this case, and there is a code-only portion to run as a script. But what it covers is when you build a model and you have a loss as a part of your forward pass, if you're training the model, then you can go and well, build the data loader with the PopTorch, which later will be helpful because we can specify the number of on-device steps in the loop inside the options class here. The optimizers are also, PopTorch Optim class are also optimized for the IPU in terms of the memory use in some cases. So you get better memory profiles with the PopTorch optimizations. And then you wrap your model with the training model construct of PopTorch. And you will have a training loop typically shown like this, where the data is pulled from the CPU for every iteration of the training loop. A command to detach from the device and say make the IPUs available for another graph to be loaded on the IPUs is this one. Can be helpful to use reuse the same IPUs for both training and inference. And model evaluation is straightforward by using this inference model construct. So probably I do not have time now during this talk to go into other things, but I encourage you to read through those other 3 tutorials on mixed precision, which is here, and it talks about numerical stability and how to configure the system to run in half precision. So you can convert your weights to half precision or weights for a specific layer. And you can make sure your data is in the same half precision that you stream to the device. And then for matmul operations, the partials can be either half or float. So you achieve an additional speed up if you use half precision for matmul partials as well. Partials meaning when you do multiplication, what is the accumulator type for the matmuls. And for the data loading, a really nice tutorial. Sorry for skipping through this quickly, that describes how the batches are constructed with on the CPU to enable this iteration on the device, more than one step in the loop, and how gradient accumulation is done when running in more than one pipeline stage or across more than one replica. And it covers the asynchronous data loading and overall recommendations, what to do if throughput is too low. So you can follow and try these steps to do that. So I think this is the main part, again, to be cautious of time. And these commands should help you run the rest of the tutorials on your own. Remember to install the requirements for the PyTorch basics 1. And the pipeline tutorial requires 4 IPUs, not 2. So that's it.